Okay, I think we should start. Projector doesn't work. Okay, I think it's coming. Yeah, so good morning, everyone. Today we will talk about probabilistic graphical models, which is a topic that has particularly large history in machine learning. It's quite early on that people started to try to model all these algorithms and techniques that we have, and the probabilistic techniques with graphs. Graphs are always very nice because they give a visual interpretation of the models that you use. They're easier to handle, right? It's easier to write some edges and some nodes than to write some formula. But we have to also know always that everything we do here with these graphs and with these little drawings, they all have to do with math. So we all have to relate whatever we draw to some mathematics behind it. And once we understand these mappings between the math and the drawings, the graphs that we use here, then it's easy to use the graphs as well, right? Then we apply mathematical rules by using graphs. And this is the powerful idea behind graphical models. So to start, I go back to a slide that we had already. This is from the very first lecture. This is the so-called Bayes filter here. This is a repetition of this. I just say this again. We have all these little steps here. I'm not going through this again. In general, what this simply does is it does two updates, right? It has an update here of what we call a sensor model, right? We have this here. And we have the application of the law of total probability, where we just marginalize out previous states. This whole thing is used for state estimation, and in many algorithms and many applications we can use this Bayes filtering. Now, what we also had already in the very first lecture is this thing here, and I think this is much easier for you and for everyone to understand, because this is something that let's say we can look at it and more easily understand what's going on, even though we might not understand mathematically what this means, right? We have arrows and we have circles here. Of course, we need to define exactly what these arrows and circles mean, but even though if we don't do this, right, we can have a much better understanding what's going on by looking at this graph than by looking at this formula here, right? This is math, and we say, oh God, what's that? But if we look at this, we say, hey, there's something going on. There's probably a time step that goes from minus infinity to plus infinity or whatever, right? We don't know that yet, but we just say there's something going on here. And there are something like dependencies, right? There is evidences here, there are some U's and some Z's here. And these arrows, they kind of always say something like one implies the other, or one depends on the other. And in fact, this is exactly what happens, right? Graphical models try to exactly interpret these statistical properties by graphs, right, with arrows and with circles. What we had already is we had these so-called Markov assumptions that there's some independence here, right? So the measurement at time z, at time t, only depends on the previous state, right? So everything else that I had before, the u's and the x before, they all don't matter as long as I know the current state, right? That means if I'm in state number t, in this state here, xt, this is sufficient to know the probability of a measurement z, right? And this is already a powerful thing, because now what this means for the graph is that there are no other arrows between to z, right? Like there's no arrow from xt minus 1 to z, there's no arrow from zt minus 1 to zt, right? So this means that only because of that, the Bayes filter, or the whole algorithm here, is very efficient. And we'll see this later, that in general we can say that the fewer errors we have, the better is our model, the more efficient is our model. But of course, every lack of an error always introduces an assumption of independency, and this might not be true, right? So we might restrict our model too strong, and then we might be estimating something which is wrong, right? So there's this trade-off of being correct and efficient, right? The same here for the states. Here we say we have a state, and the state only depends on the previous state and an action, right? So every xt only has 2 arrows going in, which is these 2 arrows and no other arrows, right? So this is already an intuition of what graphical models are, and now we try to formalize them more. And formalizing we do by definition. So we define a graphical model, which is, well, it's some kind of definition. We can say a graphical model is diagrammatic representation of a probability distribution, right? So what we have in graphical models are random variables, and every random variable is a node in that graph. And statistical dependencies, and we'll see much more in detail what kind of dependencies we're actually looking at. For now, we say some kind of dependencies between these nodes are represented using edges between the nodes, right? So if we have edges between the nodes, then there are dependencies. If we have no edges, then we have no dependencies. Now, there's a number of different graphs that we can look at, right? So in general, this is all about graph theory, and any type of graph that you could think of could be a graphical model. In general, we can subdivide these graphs into cyclic graphs and acyclic graphs, and directed graphs and undirected graphs. And in the first lesson today, we'll talk mainly about directed graphs with arrows and about acyclic graphs. And then later we'll have undirected graphs, and these also may have cycles then, right? So they will be more complicated, and we'll see that they can represent different kind of distributions. So now let's start with a so-called DAG, a directed acyclic graph. This is one, right? A very simple one. What does it mean? So first of all, we have 3 random variables, A, B, and C. And these random variables, they have these, let's say, dependencies, right? We say A, for example, does not depend on anything, right? We just say we have a distribution P of A, and this distribution is kind of independent of anything else, right? Then we have a distribution of this variable B here. This, however, depends on a value that I need to know before, right? Which is the value from A. So I have a conditional distribution here, P of B given A. And this is represented by this arrow here, right? I have an arrow from A to B that says I need to know first something about A before I can tell anything about B. And the same we can do with C here. C now has 2 dependencies. One is from A and one is from B. And these are represented in graphs in math like this here. This is a conditional probability here, the probability of C given A and B. Now these random variables here, they can be discrete or continuous, right? This is completely free, right? We choose the kinds of variables here. In general, these kind of graphs here, they are called, if they're DAGs, then we call them Bayesian networks, right? Now let's have a very simple example. In general, if we say we have k variables here, right? Then what this graph does, what this Bayesian network does, is it represents the joint probability of all these random variables. And it does it in a way that we can directly read it from the graph. So in general, the general formulation of the joint probability is, of course, this thing here. This comes directly from the equations that we had in the first lesson, I think. This is just the definition of the conditional probability applied a number of times, right? We condition on all the rest, and then we can do this again and again and again all over, so that we have, in general, this very big product here. What this means is, if we now represent this whole joint probability with this product here, right? That would mean that we have, for every product here, for every factor, we would have an edge in the graph. And what this means is that it leads to actually to a fully connected graph. Everything is dependent on everything, right? And the interesting thing is that it doesn't depend on the order of the variables, right? If we change the order of the variables, then we have, again, a fully connected graph just with different edges, right? Different directions of the edges. But in general, we can, again, represent the whole joint probability. And this is just depicted here with an example of three variables. If you have three variables, then there's all these, let's say, subdivisions or factorizations, as we call it. They're all still valid. They're all the same, right? They all represent the same joint probability distribution between A, B, and C. Now, this is, of course, very inefficient, right? We don't want that. We don't want to have these very long factorizations. Now, the trick now is to have Bayesian networks where not everything is connected, right? To model distributions in a way that we say, hey, if I know that there's some independency, some things that are not dependent on each other, then it's much better to represent it with less errors. And the fewer errors I need, the better for me for the modeling. And this is just an example of how a typical Bayesian network could look like. It has 7 variables here. And what we can now say is we can look at this graph and now say the joint probability distribution under the assumption of the independencies that I have right now, and we'll have see later exactly how this looks like. Under this assumption of the independencies, I can represent this whole joint as a product of these factors. And these, of course, are not all the factors that I had before here, right? Not all possible factors here, right? I dropped some. And I dropped the ones where there are independencies, right? What I simply did is I just went through the graph from top to bottom. And then for every node, I just write down the corresponding conditional distribution that can I directly read off the graph, right? So for this graphics, for this node x2, there's no dependency, so I can just say this is p of x2. For x1, I say this is p of x1. However, for these x4, for example, x4 has 3 dependencies, x1, x2, and x3. This is this term here. And x5 has 2 dependencies, x1 and x3, right? So what this means is that this Bayes network here represents this distribution. So it assumes certain independencies, right? For example, there's no arrow from, let's say, x1 to x3. So there is some kind of independencies here, and we'll have now more notion about these independencies. Now, in general, if we write this in general form, we can say it's this here. We say the joint probability of all x is written like this here. X is a bold letter here. X means that this is all the k variables that I have. And what I do is I multiply over all these variables, and I multiply the conditional of every variable given its parents. P, A, K is meant to be the parents of x, right? Of xk, right? So I just go recursively through this network and just multiply this thing, and then with this I have a very nice way of representing the joint probability distribution of all these variables. Now, before we go on, we have to define a number of little elements of graphical models, right? A graphical model is not only arrows and circles, because very often we have to make things a bit more compact, right? Very often we have a complicated distribution that we would like to represent, and to do that we introduce some particular shortcuts, right? This is one of these shortcuts. It's called a plate. So if I know that there's a random variable w here, and this random w influences a number of other random variables, t1 to tn, right? So those depend on w. Then to write this in a shorthand way, I can do this like this here. I say there's n numbers of these tn's, right? And they all depend on w. So I have one arrow going from w to all these nodes here, and which is then exactly the same as this here. And in math, it looks like this here. So I have, if I write this down now in a formula here, then the joint of t and w is the same as p of w times the product over all these conditional distributions t1 to tn given w, right? These are, again, for every of these here, I have an arrow in the graph. And the arrow always goes from right to left, from w to tn. Okay, now we have other elements. We might have a formula, a distribution, where we have parameters, right? Or hyperparameters. whatever we call them. So I'll talk later about the difference of that. But for the moment, we say we have some parameters, and these parameters influence our distribution. For example, we have distribution over W, and that distribution can only be written down if I have a parameter. For example, it can be a Gaussian, right, a normal distribution, and this alpha is just a mean or a variance. Right. So, and these parameters here, they're not necessarily random variables, right? They can be random variables, but then they would be represented differently. So for the moment, we assume these are parameters that are kind of given, right? They're there, we know them already, so we don't have to model them as random variables. And to do that, we introduce them as little mini nodes, right? They are not big nodes as the ones here, which are the random variables, but they are like little dots, right? A little dot is just a parameter which is a given number, right? We know that already. We know alpha, we know xn, and we know sigma square. And then we have something else, which is now we can also distinguish now random variables between observed random variables and not observed random variables. So this is a slight difference to parameters, right? Parameters are nothing that is observed. Parameters are given before we see any data. And the observed random variables, these are usually actually data points. So we represent them as random variables because they have an underlying distribution, but we observe values of them, right? That means we have some data set, and from that data set we get values for these, right? We know these values for a given data set. And there's other random variables like this W here, which is, for example, a parameter of our model. We want to learn a model that maps from input space to output space, and that model has parameters, but we don't know these parameters. We want to reason on them. We want to find a model that, for example, gives me the parameters with the highest likelihood, which is what we did in regression last week. And this is something. This is exactly here the problem. So this graph here, what we're building up here, is actually the regression task, right? So we don't know the W's, we have to reason on them, and we observe the TNs. And the observed nodes are filled nodes, and the unobserved or latent variables are written within just with a circle, which is not filled. And now, what we can do now is we have now the elements to describe the general regression problem. So this is this whole equation here. And as I said already, this is math and looks like, wow, this, right? But this graph looks much, let's say, more intuitive, right? We can now look at this graph and have more of an idea what's going on in here, right? So we have something which is observed here, which is some data that we got, and it's n times. We have this data n times. For every one of these data points, we have some parameter that influences that, which is a given input feature vector, for example, right? This very often can be another random variable, but for now we just say, hey, this is a given. We look at this as a parameter. So this means we have a product, right? Overall xn, overall tn given xn, w, and sigma square. Sigma square is this parameter here, which is our process variance. Then we multiply that with our prior distribution W given alpha, right? W is the prior over our parameters, and this distribution itself depends on the parameter alpha. And we have this distribution here, which is the distribution over new unseen data points t hat, given an input vector x hat. So I observe some new data, right, which is not the training data, some test data, which I haven't seen before. And I want to know now what's the probability of observing a t, right, given all that. And for that, of course, I need my model parameters w, and I need the again the process noise to compute this distribution. Right. So this is the formulation for the so-called for the regression problem, and we can now use that to compute the so-called predictive distribution by simply marginalizing out w. Right. We say I'm not very interested in w. Right? I only want to predict new things. And predicting means I give a new x hat, and I would like to know the probability, the distribution over possible t hats for that given x hat. And to do that, I need, of course, all the training data, which is x and t, and I need all these parameters alpha and sigma square. And it turns out that this can be done efficiently and easily with marginalization over W. Now, in general, as I said already, in graphical models we can have, yes? Question? Yeah?
Interpolated distribution, like if we have some training set and then once we're trained, we try to predict the test set. So, like, why is the arrow from sigma square going in two directions? Shouldn't it be like go on only to Tn and from Tn?
Yes, that's right. So, the question is why this sigma square goes both into the training set and into the test set. This is a particular choice of this model. It assumes that it's the same sigma for both, right? This is not necessarily true, right? Very often this is simplification of the model, right? Just to have a parameter less. But you're right, I mean, in general, you don't have to assume that, right? There can be a new model here. In this case, it makes kind of sense because predicting is nothing else than having a mapping from x to t, and this mapping, in this case, you assume that this mapping has the same parameter as the mapping for the training, right? So if you map from training points to training outputs, then you should have the same parameter then for testing. But this doesn't have to be true in general.
Shouldn't there have been a link from the Tn, which is like Tn to the t cap, like an arrow from Tn?
From Tn to T, there isn't dependency, but an implicit one. So yeah, that's right. So in general, what I said, you can always put more errors. The more errors you put to this model, the more complex it gets, and it doesn't get wrong. What you want to have is as few errors as possible, so that still represents the dependencies correctly, because then it's efficient. Of course, you can now, from all Tn's to all W's, put all these errors in there. But these would introduce more terms here, which are not necessary. Right? You try to make it as compact and small as possible. And you still have these dependencies, of course, right? You still know that Tn influences W, of course, and W itself depends on influences T, right? But it's implicit here. Okay, now let's go to the different kind of random variable that we can use for graphical models. And as I said, you can choose any kind of different random variables, but there are two cases where things are particularly efficient and nice. And these two cases are when you use discrete random variables, right? And when you use Gaussian random variables. Discrete random variables are simply, can be represented very easily with something like a histogram, for example, right? You have something like this here where you have n different outcomes of a certain random experiment. And for these, now k, I'm using k again, but this is different k now here. For this k different outcomes, you can say the probability of x given this histogram mu here, for example, is simply this here. So for every k, for every bin k, you just take the exponent, and xk is 1 when this is the right label and 0 otherwise, right? This is just the 1 out of k notation. That means just in k classes, the vector is length k, but only one of these k elements of this xk is actually true, right? That means, so I only take the probability of that certain case, right? I have 5 cases, and that case, and each case has a probability, and this is just what comes out of here, which is a kind of a mathematical description of something which is very easy, right? Of course, we have to assume, or have to know that the sum of all these weights here, there must be 1, right? Otherwise, it's not a distribution. So this is a very simple way of representing distributions. And another one is these Gaussian random variables, which we already had in the first lecture. And we'll see that if we use always Gaussians, then we have another very efficient way to represent that with graphical models. Now let's start with a very simple example, and we use discrete variables, right? Discrete variables, here we have 2 variables, and each variable has 2 different states, can have 2 states. Now, first look at this very little graphical model, right? Two random variables. There's one error from x1 to x2, what this means is now that to represent the joint, we write probability tables at every node, right? For this graph, we have this little table here, and for this other random variable x2, we need a bigger table. Why is that? Well, we need to now take into account all the cases of x1 to be able to find probabilities of x2, right? So this table is already bigger. And you can imagine, of course, if we have more variables with more errors, then these tables grow bigger and bigger and bigger. And this is one problem, of course, because the more errors I have in the graph, the bigger is my table and the less efficient is my representation. So if I calculate it, or if I want to calculate it in general, the number of table entries I need, where k is now the number of states that the variables can have, then this is our formula here, right? So of course k is 2 at the moment, but you can imagine that if k is bigger, then you only need to represent, if in this case where you don't have dependencies, you only need to represent k minus 1, right? Because the kth number is just the sum of all the other numbers, right? 1 minus the sum of all the others, right? If you just take 0, 2, then you don't have to represent the 0, 8 because it's just what completes 1. And the same is here, right? For every line here, we can do this here again. We just need to restore k minus 1, but we have to do this k times. For every state of x1, we have to do this k times. So we have k times k minus 1 plus the k minus 1 of here, which gives in general a number of k squared minus 1 lines or entries in these tables that we have, that we need. In contrast, if we look at a graph that is completely not connected, right? There's no dependency whatsoever. Then we see that we need only 2 times k minus 1, which is much more efficient, right? So this kind of shows what it means to have like not enough or not many arrows. Now, this is a more general case. We have a case with m variables here, and this is called a Markov chain, right? We have only one arrow going from every node to another node. And we can show that in the Markov chain, we need this number of parameters, k minus 1 plus m minus 1 times k minus 1, which only increases linearly with m, which is number of nodes, right? Which is nice, right? This makes things very efficient. We only need m parameters to store, right? And the number of parameters grows linearly for the number of variables. Now let's look at the other case. We have Gaussian variables. Gaussian variables in general can be written like this here. So we have a Gaussian distribution here. This is a distribution of xi, which is our variable here, given all the parents. So what we do have to do here is we have to sum over all parents, and we have a linear dependency from the parents to some parameters, right? This xj is a parent of xi, and we have some linear function here, which is given by parameters, and we also have a variance here, vi. So then, if we define this as this conditional distribution, then we can show that the joint probability p of x of all the variables is again a Gaussian, but a multivariate Gaussian, right? Which is just instead of having one variable here, we have covariance matrices and a mean vector, right, instead of a mean scalar. And furthermore, we can also show that if we express this here as this here, we say xi is essentially just this mean plus some Gaussian noise, where the noise now is very simple, right? We have now a zero mean noise with variance 1, and the variance is just it goes in here as a square here. Just we say, okay, we multiply this here with a square root here. Then, as if we can see that this is the same as this here, right? This is just another way of writing the probability of xi, right? Where we have just a constant thing here plus some Gaussian noise. Then we can see if we take now the expectation over that here, right? We do just the expectation operator. Then we see that the expectation of xi can be expressed as the expectation over its parents, right? This means that we can now compute an expectation of Gaussian, of course, is a mean. That means that the mean of every variable can be recursively computed from the mean of its parents, right? This is very, very efficient here. And the same is true also for the covariance, which I'm not showing here. So in general, what we can say is mean and covariance can be calculated recursively. And furthermore, we can say that there's other very efficient or nice properties of this graph here. The fully connected graph corresponds to a Gaussian with general symmetric covariance matrix, right? There's no constraints whatsoever on this covariance matrix, other than its covariance matrix, of course. So that means that this is, let's say, the very inefficient case. The more efficient case is if we have no connections whatsoever in the graph, and this corresponds then to a diagonal covariance matrix, right? Diagonal just means that we only have variances between the variables, that every variable has a variance to itself, but there's no variance between, no covariance between two different variables, right? Okay, now let's go a bit more in detail into the notion of independence and conditional independence. And for that, we need again our definition that we had in the very first lesson. So this is the definition again, the definition of independence. So we have a joint distribution here of two variables x and y. And if that joint distribution can be expressed as a product of x and y, then we say that x and y are independent. And if they're independent, then we can also say this here, then the conditional of x given y is the same as just x, right? This means just I don't need to know y to know x, right? They're completely independent. And we write this like this here with this little symbol here that says x and y are independent given nothing, right? And again, independence and conditional independence, they don't imply each other. No? So there's cases that do, there's one and not the other. And we'll see examples right now. So this was another notion that I also mentioned already. This is the conditional dependence. I'm repeating this again. So conditional dependence is just similar to what before. Just now we have conditioned on a certain third variable. So x and y are conditionally independent given z if you can write it like this, if we can write this as a product of x given z times y given z. And we can show that this is equivalent to these two equations here. And the notation is this here, right? X and y are conditionally independent given z. Now, let's have some examples of very simple Bayesian networks and look at the underlying dependencies and conditional independencies. So now, first of all, look at this graph. We have, again, 3 nodes, and we have arrows from C to A and C to B. This graph represents this joint probability distribution. P of A, B, and C is equal to A given C times B given C times C. We can directly read this off the graph. Now, if you marginalize out C, we try to do this, right? That means we try to compute just a joint over A and B. Then we see, and we can do some more math than that, but we can try very hard to find a formulation that says P of A and B equals P of A times P of B, but we will not find this, right? It's impossible to express P of A and B just by the product of A and B, right? So this is just one attempt to do that, and we can further try this, but there's no way to express this just as a product of A and B, right? Which means that A and B are not independent, right? They are dependent. P and A, they are not independent. And we write this like this here. However, if we condition on C, they say now we have C and we write this like this. This is an observation. We have an observation. So we say, what is the probability now of A and B given C, right? We assume I know C. What is that? Well, we plug in the definition of conditional distribution. This is this here. And now we plug in our formulation, our joint probability distribution from here, right? This is just the formula for the graph, which is again P of A given C times P of B given C times P of C. Now P of C cancels out, and we have now the definition of conditional independence. That means P of A and B are now conditionally independent given C, right? And we call this case here a so-called tail-to-tail node because the arrows, they start, both arrows start from C so the tails of the arrows are in the C node. Now we have a second example. This second example looks like this here. Now we have, again, our C node in the middle, but now the arrows go like this. They go in a Markov chain. We have from A to C and from C to B. Again, we try to find out if we have an independence relationship between A and B. To do that, we try to marginalize again over C. We have now this formulation here. P of A can be pulled out of the sum. Then we have this sum here. What we can do now here is we can put this A in here. Then we put the formulation or the definition of conditional dependencies here, which is this here. So from here to here, we simply take the definition of conditional probabilities. And so on and so on. In the end, we have something which is called P of A times P of B given A, which is obviously not the same as P of A times P of B, right? We need A here. We cannot cancel out this A here, which means, again, A and B are not independent, right? A and B are, if we use that graphical model, then the underlying random variables here, they are A and B, they are independent. They are not independent, sorry. They're not independent. Yes?
I'm sorry, but I'm not sure this line.
Which one? This one?
No, the top one.
This one?
The center. What do you mean the margin?
So this is simply a technique to find out A and B. This applies the rule of total probability. So to find out A and B from this here, what we only have to do is we take the sum over all states of C of that thing here, right? This is the joint, and now I put in front of that joint probability, I put the sum over all cases of C, right? And that gives me automatically just A and B, right? This is marginalization. We marginalize out C, right? And this is a general technique that we always use in graphical models, right? The thing is that the nice thing about graphical models is that we can ask every distribution from this graph here. We can ask P of A, of P of B, P of B given A, P of A given B. Everything that we would like to know from that graph, we can get with marginalization and with very simple rules from probability theory, right? There's only two rules actually that you ever apply. And it makes sense to really know these rules well, right? Now, let's look at the same graph again, but now we'd like to say, I observe this node here, right? Now, again, we want to analyze the case where we condition on C, right? Now, instead of having the joint here, we have just A and B given C. We do this again here. We have our joint divided by P of C, which is the definition of this here. Now we plug in the formulation from the graph, right? This joint represents just P of A times P of C given A times P of B given C, which is this here. And now we can say that I think we have to play base rule here again. This is then A given C times P of C. Then P of C cancels out and P of A cancels out. So from here to here, there's a little step here, which I give you as an exercise, but it's a very small step, right? This is just applying base rule to P of C given A. Then things turn around and cancel out. So in the end, we have this formulation here, which is exactly the definition of conditional independence. That means A and B are conditional independent given C, in the case that this graph looks like that. So we have, in this case, we call this a head-to-tail node, right? Because in the node C, we have one head of an arrow and one tail of an arrow. And now what's missing is of course, the third case, which is this one here. You can already guess what this called is. This is, of course, a head-to-head node here, a head-to-head case. Now we do the same again. We try to find, would like to know if A and B are independent, right? In general, without condition. And it turns out, yes, they are. And why is that? Well, we do the same as before. We have our joint here. We marginalize out C, right? We sum over all values of C. We can pull out A and B from this here, right? Because they're independent of C. And this thing here, right? This is just the sum over all values of C of a distribution of C given anything. And this is always 1, right? Because it's, by definition, it's a distribution. So the sum over all C of this thing must be 1, right? So this means that we have proven that that A and B are independent, and we write this like this here, right? They're independent. However, if we condition on them, it turns out that they're not conditionally independent given C. And this is the same argument as before. We try to plug this in. We try to deduce the formulation for conditional independence, but we won't find any, right? We try this here. We can do more calculations on that. You will not find a formulation that says P of A and B given C equals P of A given C times P of B given C. So we have the result that A and B are not independent given C. If we condition on C, then they are not independent. And as I said already, this is the so-called head-to-head node. Now, we can summarize all these three cases and now ask ourselves, when does the graph represent conditional dependence and when does it represent independence? And in general, we can say in tail-to-tail case, it represents conditional independence if we condition on the tail-to-tail node, right? If we condition on the tail-to-tail node, then we have the independence, right? In the head-to-tail case, it's the same. If we now condition on the head-to-tail node, then we have also independence. However, in the head-to-head case, it is true in the opposite case. If we do not condition on the head-to-head node, on the C node, and neither on any of its descendants, which you haven't shown here, but which is another thing that can be proven, then we say that they're independent, right? In general, this leads to the notion of so-called d-separation for directed graphical models. And d-separation, this is the definition of d-separation. In general, we have, instead of single nodes, we have subsets of nodes. So we have A, B, and C. These are non-intersecting subsets of nodes in a direct graph. So they can have many, many nodes in A and B and C, but there's no node which is in more than two of these sets, right? They are completely non-overlapping. Now, we define a path from one of these sets of nodes to another set of nodes. And we say that this path is blocked by any node of in the set of C if C contains a node such that either one of these is true. First, either the errors on the path meet head to tail or tail to tail, which is the first case, and the node is in the set, so we condition on C, or the errors meet head to head at the node, and neither the node nor any of this descendants. So the errors meet, but this node in the set C, we don't condition on it, and we don't condition on any of its descendants. We'll see in the next slide how this looks in graphs. So that means we have now a definition of blockedness. That means we can say if a path from A to B is blocked, if any of these conditions is true. And then we can say now if all paths from A to B are blocked, then we say that A is d-separated from B by C, right? And we notate this like this here, d-sep from A and B given C, right? Any path from A to B is blocked by C. That means that A and B are d-separated by C. And the most important thing to take from this is a property only on graphs. This does not tell anything about distributions yet, right? This is an algorithm that you could implement. I give you a graph representation, and you just implement something that checks these things, right? Check every path from A to B for a given subset of A and B. Look if all the paths are blocked. If all the paths are blocked by C, then you say this is d-separated, otherwise it's not, right? There's nothing said about distributions here, which is the nice thing, right? The idea is now to relate this d-separation relationship between three subsets to a property of the distribution, which is conditional dependence, right? And I'm giving a small example before the break. So this is one example of d-separation to make it a bit more clear what this means. So we have 5 nodes here, A, B, C, E, and F. D is missing for whatever reason. We say, if we now look at paths from A to B, we would like to know if the node C d-separates A and B. So when does it do that? Well, if any path from A to B is blocked by C, and it's not blocked by C, right? Because we don't condition on this node here, but we condition on one of its descendants, right? This is this kind of tricky case where we have to look at if every path, or if the path from A to B, right? If there's a node on that path where we condition on, and that node is a tail-to-tail, is a head-to-head node like this one here, then the path is blocked. But also, if we condition on any of its descendants, this is kind of complicated. But I hope to clarify this with this little graph, right? If this thing was longer, and they're all white nodes here, not filled nodes, but the last one is conditioned on, then we have again that this thing is not blocked, right? So it's not deseparated. A and B are not deseparated by C because we condition on C. However, if we have the tail-to-tail case, like here, there's one node on the path between A and B, which is a tail-to-tail node, and we condition on that node, then we know that the path is blocked and it's deseparated, right? And I think we stop here and do a break if there's no questions. Okay, let's go on. We have talked about deseparation, and we have said so far that deseparation is just a property on graphs, right? That makes it easy because we can now have nice algorithms that test on deseparation. But the whole purpose of that, of course, is to define, to find conditional independence relationships between the nodes. And to do that, we need another kind of mathematical notion, and we do this stepwise. So first of all, we define what an IMAP is, an independence map. A graph G is called an IMAP for distribution P if every deseparation of G corresponds to a conditional independence relationship satisfied by P, right? This is the definition of an IMAP. What this basically means is that for any kind of triple A, B, of C, of nodes in that graph, it holds that whenever these A, B, and C are deseparated, so if you say A is deseparated from B by C, if for all of these deseparation relationships, it is true that A is conditionally independent on B given C, then we say that this graph is an IMAP, right? That just maps all deseparations to conditional independence relationships. And a very simple example of that is the fully connected graph. The fully connected graph is an IMAP for any distribution because there are no deseparations, right? Because the fully connected graph, you will always find a path from A to B because it's fully connected. So there's no blocking and no deseparations. That is, by definition, then any deseparation represents a conditional distribution, independence relationship. That means if we don't have deseparations, then trivially we don't have to look at this, right? This means the fully connected graph is an IMAP for every distribution. Now we can see through the opposite. We can now define what a DMAP is. A DMAP is a graph that is like a graph is called a DMAP for distribution P if for every conditional independence relation satisfied by P, there's a deseparation in G. So this is the opposite way, right? Now we say, if we know that A is conditionally independent given of B given C, if for all these relationships of independence, it is true that we find a deseparation in the graph, then we say that this graph is a DMAP, right? And here again, the opposite example, the graph without any edges is a DMAP for any distribution, because all pairs of subsets of nodes are deseparated in that graph, right? So we have anyhow, so that means if the underlying distribution has any kind of independence relationship between A, B, and C, then it is already represented as a deseparation because everything is anyhow deseparated, right? Whatever kind of three kinds of nodes A, B, and C we take, they're all deseparated. That means whatever we have here, it is represented already as a deseparation. And now, of course, these two graphs, these two extreme cases, are not very interesting. What we actually want is a so-called perfect map. A perfect map is both a D map and an I map. And this is the definition of a perfect map that simply says a graph is a perfect map if for any relationship of conditional independence we have d-separation and back, right? So every d-separation is represented uniquely by a relationship between A, B, C as a conditional independence. So this now is a way to map between the world of graphs to the world of distributions, right? A perfect map uniquely defines a probability distribution, right? We have a joint distribution over a set of variables, and that probability distribution can be uniquely defined by a graph, which is a perfect map for that probability distribution, right? And we'll see later examples of this perfect map. This is just a formal way of mapping from the world of distributions to the map of graphs. One more note before we go on to a different kind of graphs. This is kind of an important notion here, which is called the Markov blanket. The Markov blanket arises in the following case. Assume that we have a very big Markov Bayesian network with many, many nodes here, like more nodes than these here, right? And what we'd like to know now is the distribution of a given set, a given variable xi, conditioned on all the others. Right? So now we have, let's say, hundreds of nodes here, and we condition on all the nodes but xi. Right? This is an operation that is used very often. Right? We just pick one of these and say, what is the probability of seeing that or have a distribution of this particular node if I assume that I observe all the rest, right? I condition on all the rest. Now, if I write this as a formula, this is first the definition, of course. That means this is the joint over all variables. And this here is the joint, but with the difference that we marginalize out over xi. So this integral here is in the general case where we have continuous variables. In the case of discrete variables, of course, this would be a sum, right? We sum up over all variables of xi, right? And this is what I said already. This is the operation of marginalization, which would then mean that the resulting distribution of this is a joint over all but xi, right? So if I divide this by this, then I get exactly this here. This is the definition of conditional probability. That means the joint over all divided by the probability of what is on the right side, right? This is the formulation for that. Now, what we do now is we plug in now the definition of our Bayes network, right? We say the joint of all these variables here can be represented as a product over conditional probabilities, right? The product over all nodes, and at every node I take the conditional of xk given its parents, right? This is the definition or the representation of a Bayes net for this joint probability distribution. And of course the same here, right? The same is, we just plug this in here in the denominator. Now it turns out, if you look at this very closely, then it turns out that in this lower term here, we sum over all these xi. That means that all the other terms that do not depend on xi can be pulled out of this integral because they don't depend on xi, right? That means we can now imagine that this is a long product of factors, and all the factors that where there's no xi in there can be pulled out and put in front of this integral. But of course, for all of these terms which don't depend on xi, there is a corresponding term in the numerator, which means we can cancel them out. Right? We just cancel all these terms where there's no xi in there, we cancel them out. And as a result, we will have a joint probability distribution here over all variables that have something to do with xi, which is xi itself and its parents, but also all the children of xi with their parents. Right? Of course, these are all the terms that we need. And in the numerator and the denominator, we have the same, just with xi marginalized out, which is just all the nodes but xi. And this again, we can write it like this, right? This the conditioning, this joint probability or a condition on is just all the nodes, but xi, right? Is this kind of clear? How this comes from? So in general, we can say if we have a Bayes network and we'd like to compute the conditional of xi given all the others, we only have to look at the so-called Markov blanket. The Markov blanket is defined by all the parents of xi, all children of xi, and all so-called co-parents of xi, which means all the parents of children of xi, right? If we condition on all them, then it's sufficient. We don't have to condition on all the others, right? Because there's an conditional independence relationship between xi and all nodes that are not in the Markov blanket, given the Markov blanket, right? This is interesting and nice. We can use that now because those things make much more efficient. But we'll see later that it can be done even so. If we have other models, then this would be even easier to use this thing. So now, first I summarize this first part, which is on directed graphical models. So first of all, graphical models, they represent joint probability distributions using nodes for the random variables and edges to express the conditional independence. A probability distribution can always be represented using a fully connected graph, but this is inefficient, right? So adding more edges to any graph is no problem at all, right? It's just if you model your problem with too many edges, the only thing that can happen is that it's very, very inefficient, right? So the reasoning on that is very inefficient because you have to represent more parameters, and this is a problem. So the goal is to find good models which have few edges but still work well for your model what you like, right? If you have your distribution that you would like to model with a Bayesian network, then try to find one that still represents the problem nicely with as few edges as possible. So and then we have these called DAC, the directed acyclic graphs. Here we can find a conditional independence using deseparation, right? And we do that using so-called perfect maps. So we assume that we have a perfect map of a given distribution, and this perfect map then implies a one-to-one mapping between relations and distributions. And then we can now, instead of looking for conditional independence relationships in the distribution, we just look at the graph itself and look for deseparations in the graph, right? And this gives me then, if we have a perfect map, then this gives me automatically exactly the three tuples that are conditionally independent. And lastly, we said the Markov blanket is defined by the minimal set of observed nodes to obtain conditional independence, right? We only need to condition on them to find the condition on all the rest. Now, this was all directed graphs. Now we go on with undirected models, and we look again at our Bayesian network. So we have this was the example from before, from the last lesson. We would like to, this can be used to generate samples from it, but there are some problems. First of all, deseparation was, the definition of deseparation is, let's say, not very intuitive. It's okay, it works, we can use it, but this little exception here with the tail-to-tail node is not very nice, right? We don't really like this very much. And if we go into more detail, the problem with that was the head-to-head node. And if we look at the very detail, what happens at this head-to-head node, we have a little example here. So this is example also from the book. We have three variables. One variable A is represented by a battery. Battery is charged, which is 0 or 1, so all variables are binaries. Then we have variable B, which is a fuel tank, and the fuel tank is full or not, 0 or 1. And we have something that measures how full the fuel tank is. So we have a gauge that says it's either full or not. And again, we have a binary variable. And now we would like to do reasoning on that. So we have some example numbers here. Let's say the prior probability of battery being charged is 90%. The fuel tank is 90% full without knowing everything. And we have this little table here that represents P of C given A and B, right? So for every state A and B, we have a probability of C. So now let's do some reasoning here. Now let's say we compute first P of not C, right? I could do this here, but I'll also leave this as an exercise. As I said, we can compute from this graph, we can compute all different distributions or probabilities that we'd like to have. To do this here, we have to, again, marginalize out over A and B, right? What this means is we have the joint here, P of C given A and B times P of A times P of B, which is the whole joint probability distribution. We can write this down, and then marginalize out over A and B, and then do 1 minus that, and we have the probability of not C, which is turns out to be 31.5%, right? This is the probability of not, that the fuel gauge says it's empty, right? This is the probability. Now, the same we can do for this probability. We can say, what's the probability of the fuel gauge is empty given the fuel is actually empty, right? So how likely is it that if I know that the fuel tank is empty, there's nothing in there, what's the probability then that the fuel gauge says, yes, it's actually empty? And it's quite high, right? This is a good number here. 81% says, yes, it's empty then. Or it says empty. With that, using again Bayes' rule, we can obtain this thing here, right? Which is roughly 25.7%. And now let's look at more deep detail what this says. This says, if my measurement of my fuel gauge says it's empty, what's the actual probability that it's actually empty, right? This is the opposite, right? This is, as I said, the reasoning methods here. We now say we see a measurement, and based on that measurement, we'd like to find this is the actual reasoning that we actually want, right? This is the real case that we usually have, right? And we see that with a 25.7% probability, the fuel tank is empty, right? So I look at my meter and it says empty, and with that probability, it's actually empty. However, if we now compute this thing here, right? The only difference between here and here is that we now also condition on A. We say the battery is empty and the fuel gauge says it's empty. Then it turns out that the probability of being empty is even lower. And that's very surprising, right? But it kind of makes sense because now I know that the battery is empty. The fact that the battery is empty explains away the fact that the fuel gauge says it's empty, right? So there's another reason that explains me why this should be the case, right? This A influences C. It says, well, when the battery is empty, then of course my meter doesn't work. And if it doesn't work, then I have less a notion of what's actually happening, right? So the probability of then being empty is less, right? Because A is a better explanation of it, right? It explains C away. I don't know if this is clear, right? There's this little difference here. And this only happens in directed graphical models, where there's an error between A and C and B and C. Only in these head-to-head node cases this happens. And this is kind of odd. We don't want that. Then this is again deseparation. Let's go and find ways where we can have models that don't have these kind of subtleties, these problems. And the idea is to use so-called undirected graphical models. So the motivation of undirected graphs is simply, first of all, we have this deseparation thing, which is a bit hard to define. And the question is there a simpler or more intuitive way to express conditional independence in a graph than with deseparation? And can we find a representation for cases where an ordering of the random variables is inappropriate? For example, if we have pixels in a camera image, and every pixel is a random variable, then it's hard to define a Bayesian network on these pixels because there's no ordering on these pixels, right? And we can do this by using so-called undirected graphical models, or they're also called Markov random fields. And these are these two examples. So on the left, we have made the attempt to represent a camera image with a graphical model, right? With a directed graphical model with arrows, which really doesn't really make sense. Why should this pixel influence that and not that, for example? And why is there no arrow backwards and stuff like that? So this is not really intuitive. That's one thing. And the other thing, the Markov blanket, on this xi thing here, as we said already, is defined by the parents, by the children, and by the co-parents. This is children, this is co-parent. That means these two co-parents, they need to be conditioned n as well. And it's not really intuitive why this should be. However, as we will see later, the Markov blanket, or right now we'll see this, the Markov blanket of an undirected graph, if you just remove the edges, is just that. It's just the neighbors of xi, which is much more intuitive, right? We only have to condition on the neighbors of xi to find the conditional of over all possible, over all nodes. So, and here we try to, or we define the same notions of deseparation and blocking paths for undirected graphical models. That means, sorry, if we have now three subsets of nodes, A, C, and B, now things are much easier. If you now want to find paths from A to B that are blocked by C, then it's very simple. We just have to look at if any path from A to B goes through C, right? Through a node in C, then we say that this path is blocked by C, right? Now it's very easy to look at paths being blocked between A and B, because now we don't have to look at any children of C nodes and stuff like that, right? And as I said already, the Markov blanket now is much easier as well. Okay. Now let's look at a bit more in detail how we can now factorize, how we can formulate this mathematically, this Markov random fields. And there's an interesting observation. So let's look at first. We have an example of two nodes, xi and xj, and we assume that xi and xj are not connected, right? This might be, for example, this one here and this one here, or this one here and this one here. They are not directly connected in the graph. That means that they're independent, right? Because that's conditionally independent given all other nodes. And why is this the case? Well, if we say, if we write this down here, xi and xj given all the others, then we know that any path from this node to this other node has to go through a node which we condition on, because we condition on all others, right? So here this is just xi and xj conditioned on all the others. That means that in our C set now we have all the nodes but xi and xj. That means that every path from xi to xj goes through a node in C, which is then blocked by C. That means, again, that xi and xj are independent given all the others. And then the next observation is, in turn, this means that each of these factors here, contains only nodes that are connected. Why is that? Well, if they're not connected, then again they're independent and they're in different factors. Right? That's a very nice observation from independence to factors. That's the reason why we actually use factorization in Markov random fields. It's a very clever way of doing that. Right? So every factor here necessarily needs to represent a fully connected subgraph. Because if there's any two nodes in that factor which are not connected, then if we condition on all the rest, then we have paths that are blocked, and that means they need to be in different factors. Right? Is that clear? I hope. This is the main observation of Markov random fields. That means that our joint probability distribution is now a set of factors of fully connected subgraphs. And these fully connected subgraphs are called cliques. Right? This is an example here of a clique. So we have a green clique, which is just two nodes, and all nodes in that little clique are connected with each other. Okay, we have just this one edge here. But there's bigger cliques, that is these three nodes here, right? And they're all interconnected with each other. And these are called maximal cliques. Maximal cliques are cliques that cannot be extended by another node so that they're all connected, right? We cannot add this node here to the maximal clique because there's no connection between x1 and x4. So the maximum clique in this graph is this one here. But of course, it's not the only maximal clique. There's another maximal clique here, right? There's a 3 clique here and a 3 clique here. Now, the idea is to represent the joint probability distribution as a factor of cliques right? For every clique in the node, we define a factor, and then we multiply all these factors into a big joint. This is the definition of a Markov random field. This is here. So definition of a Markov random field is, in general, if we have a joint probability distribution over X, then we can represent that as a product over factors phi C, right? Where C is the set of all cliques in the graph, the set of all maximum cliques in the graph. This is important, right? So maximum cliques in the graph. For every maximum clique, I have something that's called a potential. And the interesting thing is that this potential does not have to be a proper distribution. It can be just any positive number, positive function on these cliques. Because what I do is I normalize in the end. I then divide by z, and that is just the sum over all x prime of the same thing, right? I just normalize the enumerator, yeah, by again summing up over all values of x prime, right? This is called the partition function, this z here, and it's usually very hard to compute that. But in many cases, I don't have to compute this because I do maximum a posteriori or maximum likelihood estimation, and I only need the maximum, and this z is independent. This is just a number, right? So if I maximize this thing here, if I use, for example, I look for parameters that maximize this whole thing, then I only have to look at the at these phi functions here, right? Now there's a very important theorem from Hammersley-Clifford that says any undirected model with associated clique potentials phi c is a perfect map for the probability distribution defined by this equation, right? So if I am given a Markov random field defined by these graphs here, right? And now for every maximum clique, I define my nice phi function, my potential. Then these potentials already represent a proper distribution. This is a strong sentence, right? Because this just maps from graphs to distributions, right? And they're all defined well here, right? There's a probability distribution that can be directly read off the graph. I take the graph, define some potentials to the graph, and I already have a Markov random field. And as a conclusion, you can also say that all probability distributions that can be factorized as here can be represented as an MRF. So there's a one-to-one mapping between these two, right? We say, if we have a distribution that can be written like that, then we can write this as a graph, right? We don't have to do math, we just do drawings, which is much nicer than math, right? Okay, now in the next couple of slides, I just want to talk about the dependencies or the differences between directed graphs and undirected graphs, and how can we express and how expressive are they compared to each other. So first of all, we observe if we have a very simple case like this here, the Markov chain, then we can convert that directed Markov chain easily into an undirected Markov chain, where we simply say every term here just represents a factor, right? And the factor is nothing else than a potential in the Markov random field, right? So these potentials here are functions of maximum cliques, and the maximum clique is 2 here in this case. So every clique here has a potential, right? And these potentials, if I map them with these probabilities here, then I have exactly the same distribution as I had for the directed case. Of course, I have to normalize that because these are probabilities and these are not probabilities, but in this case, I can just say z is equal to 1 because trivially, these factors are already proper distributions, proper probabilities, right? So I don't have to normalize them again, right? Which is nice because now we have a much more general formulation of that. This 5 thing doesn't have to be a p, but if it is a p, then it's also fine, right? Then we are happy. Now we try more to get an idea of what's the difference between directed and undirected graphs. If we have this undirected graph, we would like to convert it into an undirected graph, then things turn out not to be so easy anymore, because these conditional distributions here, they are usually mapped into cliques. And the problem is that we have here again a head-to-head node, and the variables are not conditionally independent given this head-to-head node. That means this cannot be represented in an undirected graph. This the fact that xi and x3 are not conditionally independent given x4. Because if we do this here, then they are, right? If I condition now on x4, then they are conditionally independent. And to represent that, I need to do a little trick here, which is called moralization. So instead of just, in addition to always just removing these arrows, I marry the parents. This is called moralization, right? In this case, parents are not married, and I just put them together, and now they're married. And now there's a node between the parents of x4, right? Now it's moralized. Which in this case, of course, leads to a fully connected graph, right? And this is not exactly the same as we had here, right? There are now independencies lost, which is bad because this is very inefficient. This is what we have on the next slide, right? This is the problem here. We add edges here, but by adding every edge, we lose independencies. And losing independencies always is bad for inefficiency reasons, because now we have this fully connected graph, right? And we have to represent this with many more parameters, and doing reasoning on this graph is more inefficient. But in general, we have to say there's no one-to-one mapping. We cannot, in general, have a directed graph and map it into an undirected graph or back, right? There's just no way of doing that. And this is shown in the next slide. This just shows the representability. This just shows the set of all directed graphs. Sorry, the directed graph is the green one. The set of all distributions that can be represented with a perfect map as a DIG, with the directed graph, right? This is the distributions that are represented by directed graphs. And the green one is the set of distributions that are represented with an MRF. And you see, of course, there's a lot of points in the middle here, right, in the intersection. That means we have the possibility to represent some of the distributions with both kinds, but there are cases in each direction, right? There's cases that can only be represented with an MRF, and other cases that can only be represented with a directed graphic model. And even worse, there's cases that cannot be represented by any graph, right? There's just no way of reading this. This is another example on this how we represent conditional independence. So we have here this graph represents an independence but no conditional independence. And if we'd like to now represent the same set of independence relationships in an undirected graph, then we can't do this, right? This is an example where these two independence relationships can only be represented by this particular graph. And if you try to convert it to an undirected graph, then we have other independence relationships here. And these again cannot be represented in a directed graph, right? There's no way of representing that. So that means that we have to be careful which kind of model we choose when we want to model independence relationships, right? So depending on your problem, it might make more sense to use an undirected graph, a directed graph, or use an undirected graph. And now in the last couple of slides, I would like to already start to say how we use these graphs, right? So far we only defined how graphs look like and how we can model independence with these graphs, but how do they actually use that? What can we, or how can we use them to do some machine learning with that? And the most important task in machine learning very often is the so-called inference, right? The inference step is defined as something that that does some kind of prediction for a given set of data, right? So what this means for graphical models is that we say we have a graph, and we say some of the nodes in that graph are observed, right? These are the data that I get. And from that, given these observations, I would like to find a distribution over some node in this big graph, right? A marginal distribution over xn given these observed nodes. This is definition of inference for the particular case of graphical models. But inference is a general problem in machine learning, and we'll see other machine learning techniques where we where the inference task is the one that we actually want to solve, right? This is where we do prediction from training data. Now the question is, how can we do inference with a graphical model? And we'll now see a very simple example of a graphical model and already define a good algorithm to do inference in that graphical model. So let's look again at this Markov chain here. This is an undirected Markov chain here. And this is just the copy from above. So we have these 5 nodes here. We can represent this Markov chain here with a number of factors here. These are 1, 2, 3, 4 factors for every clique, which is just a pair, right? Every pair in this graph we have a potential. And of course we have to normalize that in the general case. Now, inference is one example of inference is to find the marginal distribution at a given node. Let's say we want to have the marginal at this x3, right? The marginal of x3 is just defined by the probability of x3, right? Which is nothing else than marginalizing out all the others, right? I take the joint, this whole joint thing here, and I sum up over all potential values of x1, x2, x4, and x5. Not x3, of course, because x3 is the one we would like to have, right? So now this is just, you can interpret this as we have information about all these other nodes, and given all these other nodes, what does this information of the other nodes bring us for x3? It's not conditional, it's marginal, so it's not given. It's just saying, like, introducing all this knowledge is what we have here. What do I know then about x3? And in general case, with n nodes, of course, we have this very long thing where we have, instead of 5 or 4 potentials, we have n minus 1 potentials, and we have n minus 1 sums here, right? We sum over all other variables but xn. Now let's do this. They have this 4 sums here again. The problem with that is this would take k to the n computations, right? We have, with every sum here, we have another potential here, another exponent here in the number of computations. And this is very inefficient. But we can do this because we have this very efficient representation here, which is a chain. We can do this much more efficiently simply by rearranging the sums. So this is a very little neat trick here, right? We have these 4 sums here. And the only thing we do now is we switch these 2 sums around. x1 and x2 are just swapped. We can do this because it doesn't matter in which order we sum this, right? In a set of many sums here, this is just the general rule. We can just swap sums here because the order in which we take these sums just doesn't matter at all. And now, once we have this thing here, now the particular structure of our network comes into place, because now we have only dependencies between direct neighbors. All the others are gone, and this makes things very efficient. And why is this? Well, now we can observe that, for example, this potential 4, 5 here, right? This only depends, of course, on 4 and 5. That means that all the others, like 2 and 1, 2, 2, 3, and 3, 4, they can be pulled out in front of the sum over 5, because only this one depends on x5, right? So we can put this sum here over x5 just in front of x4, 5, 4, 5, right? All the others don't depend on it. And the same holds for x4. This sum over x4 we can be just put in front of this one here. And the same for x1 and the same for x2. So in the end, this is the same sum as before, just with different orderings. Just the sums are now placed differently. And now we see that things are much more efficient, because now we can do this recursively. Now we start with this potential here. We compute a sum over these k value of the states, the number of states, k states that we have. Yeah? And then we have a vector here of k states, and this vector goes into the next sum, and this goes into the next sum and the next sum, right? So another way of writing this is, this whole thing here is everything before x3, right? This is 1, 2, and 2, 3, which are potentials before we observe, or we would go to 3, from left to right. These two things, these two sums, can be written as a vector of length k, right? Because we just go over all the states of x3, and for every state of x3, we sum over x2 and we sum over x1, right? So that means we have a vector that gives me for every state of x3 gives me a number, and this number is computed by sums here, recursively. And the same is here, right? So we have vectors here and vectors here, and now we simply have to multiply these vectors together to get our probability here, right? and in general, we can interpret this as something called a message passing algorithm. So every vector that comes from a node here to a neighbor vector can be interpreted as a message. And this is the general case here. We have n nodes here, and if we marginalize out all the nodes but xn, then we can say in general we have a recursive formulation for messages that go from one node to the other. So these messages travel from x1 towards x1, xn in the positive side, and these messages come from x big N to x small n from the opposite side. Right? These are again messages which are simply represented as vectors of a length k, where k is the number of states of the variables. Right? We have discrete variables here, and they have k states, and and we can use this. So this gives us a very efficient algorithm, right, to recursively compute these messages. So this message alpha of xn can be written like this here, where all this rest here is nothing else than the message that has been done before, right? The message that came before into that node xn minus 1. And the same is here for the next ones, from n plus 1 to n, right? The same is here. The mu beta message is simply again a recursive formulation here from the message that comes into the next node xn plus 1. That means in general, computation of mu a starts at the first node, and the computation of mu beta starts at the last node. Yeah, so this is what happens here. Now we have to, of course, compute the messages from the first and the last node itself, but these are very easy because they don't depend on anything, right? This mu alpha here of x2, this is the message that goes into the node x2, is defined by the marginalization over all values of x1 of the potential between x1 and x2, right? We take the potential of x2 and x1, marginalize out x1, and we get the message that goes into x2. And the same for backwards, for n backwards to n minus 1. And another observation is that to compute z, we can do this at every node, right? Once we have computed all these messages between the nodes, right? And of course, we have now messages in both directions, right? We can now compute the messages from mu alpha from here to the very end, and also betas from here to the very beginning. So at every edge, then, we have two messages, one going to the right and one going to the left. And with these messages now, we can now compute the partition function by simply marginalizing out the particular node. Let's say we have one xn here. We take these two messages that go into that one, and then we just sum over all states of this, which is basically just a dot product, right? This is just dot product of this vector times this vector. In the end, what this means is that the number of computations we have is O(n) k square, because at every potentially we have to do k computations and k sums. So we have to, for every state of x2, which is k states, we have to do a sum over k states, right? So this takes k times k, and we have to do this n times, right? N times k square, which is much more efficient, of course, than if we had the fully connected graph. Yeah, this is just a summary, I think. To compute the local marginals, compute and store all forward messages, right? All alpha messages, then we store all backward messages. Then we compute z only once at a given node, right? And now we can just compute our marginal, right? Now we have everything in place. We just take these two vectors to the dot product of them and normalize it, and that's it, right? This is doing inference on a Markov chain. Yeah, let's summarize also the last part of this lecture today. We have seen undirected graphical models. These are also called Markov random fields. They provide a much simpler method to check for conditional independence, right? We don't have to have this complicated notion of d-separation. We just look at the graph and see if every path from A to B is blocked, and being blocked is much easier to check than for directed graphical models. An MRF is defined as a factorization over clique potentials, and it is normalized globally, right? So that's another difference from directed to undirected models. The undirected models, they don't have to have proper probabilities, right? They can be functions of cliques that are just positive, because the normalization is done anyhow globally in front of it. So I have to do the normalization, of course, to get a proper distribution, but this normalization can be just done in front, and very often we don't even need it because we do maximization. Now, direct models can be converted into undirected models, but it's not so easy because very often we lose information or we add complexity to the model which is not necessary, right? So either we lose things, which is bad because then we cannot represent our distribution well, or we add things to it which makes it more complex, which is also not what we want. So we have to be very careful when we convert one to the other. And then for undirected Markov chains, we have seen there's a very efficient inference method that is based on message passing. And next lesson we will talk more on message passing, because this message passing algorithm here basically is this algorithm here, right, where we compute for the messages and then backward messages and then Z. It's a very simple algorithm, but it can be extended to more general graphs. And this will be done next week. Thank you.